Okay, so let's move into the lecture number 10, worksheet number 10. So now lecture number 10, we talk about the electricity. So we start with some basics information about the electricity, like electric force, electric field, electric potential, and then we move into the electric potential and the current. That's where that we can discuss about the connection of the devices like your light bulbs or electric resistors, heaters, those electric circuits in your class. Very simple version of those electric circuits was our final conclusion of this electricity part, right? So we start with the Coulomb's law. If you watch the lecture, you probably remember those things. So we talk about the Coulomb's law, right? So Coulomb is the scientist that discuss about the force between two particles. So if you have two charged particles, Q1 and Q2, these two particles, if they are sitting on distance R, these two particles feel the force. That force is given by Coulomb's law. That force, magnitude I'm writing, will be equal to some constant, that we call it as Coulomb constant, charge of one particle and charge of second particle, and divide by the distance power, right? So what that means is basically force is proportional to Q1 and Q2, and also force is proportional to 1 over R to the power 2, right? That's the idea, right? So now this force can be attraction force or repulsion force, depend on what particle you have it on the system, right? If they are positive charges in this case, that means I have the same sign charges, they're going to repel. So that's the force that I am calculating. If they are positive and negative, they're going to attract to each other, right? After we went to the Coulomb's law, we discussed about electric field. So electric field is defined it as K times 1 of the charge divided by the R squared. What that means is if I have a charge particle Q, if it is a positive charge, we'll say it is a positive charge. If you need to find the electric field somewhere in here with the R distance, that is what the formula that you can use. If it is a positive charge, it will create the electric field outward direction. If it is a negative charge, it will create the electric field inward direction. And next part we went is the electric potential will be KQ over R. What that means is if you have a particle, we'll say here positive charge again, and if you need to find the potential somewhere here with your distance, that's how you find the potential. Only difference you see that R is squared, here R, right? So now these two that we discuss are vectors. This is a scalar quantity. Okay, so check back for the units and those things in your lecture part. After we finished this one, we went to the electric current. Current is basically charge per unit time. And then we move into the resistance, capacitors, and we solve very simple circuits by using those informations. Okay, so we will discuss that throughout the worksheet. Okay, now first, let's move into the your first question number. So how many electrons are in 2 coulombs, right? So now to do that, you definitely should know the charge of the electron. So charge of the electron will be equal to 1.602 times 10 to the negative 19 coulomb is the unit of the charge. So now if I need to find number of electron in 2 coulombs, that means I need to divide this 2 coulomb by the charge of the electron. Then you will get the number of electron. Coulomb will cancel out. Then you will get the answer 1.248. 10 to the 19. That's what I have as number of electrons. Okay, now let's move into the second question. So second question is directly understanding of Coulomb's law. So you have two charged particles, does not give the what is the charges are, we'll say Q1 and Q2, right? They are sitting on distance D, right? And it called, there is a force F, right? And now what you're going to do, now you're going to keep your Q1 as it is, but you're going to drag your Q2 to the distance 3D now, right? Now there is a force, that force we're going to call it as F new force, right? So now definitely we know that when your particles are go away, because it is 1 over r, when the distance is greater, your F is weaker, because going away from the particles, F is getting weaker and weaker. So we know that it is decreased, but how much? What will be the force on each other now, right? So now first case, we know that F will be equal, let's write the constant, those all are constant for this problem. And then I have 1 over D power 2. I write the 1 over D power 2 separately because I can easily understand the difference, that's why. So nu equal, again, K, Q1 and Q2, you did not change. Only thing you change is you make a distance 3D now, 3D and power 2, right? If I simplify this, K, Q1, Q2, and I have 1 over D squared, but I have 3 to the power 2, that means I will left 1 over 9 amount, right? So now if I compare the formula that I have earlier and now, you will see here I have this formula. This is exactly same as this part. That means you have extra term, 1 over 9th is the change that happened because of the your distance increase. That means what happened? Your new force equal 1 over 9th of the your old force. Okay, now let's move into the next question. So now I need to find the magnitude and the direction of the force at Q1. So this is to understand the your vector informations again, right? So now you see that what it's asking. So net force on Q1. That means this is your point of interest. Point of interest is the place that you need to draw the free body diagram, right? So now do that. I need to understand, let's label the point of interest. It is here. Now I have two particles, one on the left, one on the right. Now I need to see that it is attraction force or repulsion force. According to that, we need to draw the diagram. Okay, let's start from the left one. So you see that in the left one, Q2 is a negative charge and your point of interest has positive charge. Now negative and positive will attract each other. Because of that, I do have the force. I'm only drawing the free body diagram on my point of interest. Let's label it as F2 because of the Q2, right? So now if I think about the right particle, this is a negative and this is positive. Because of that, these two also will attract each other. Then it will create the force in this direction. I don't know which one is greater yet, but these are the two forces I have, right? So now if I need to find the net force, that's what the question is asking. So net force will be equal to the right direction, right? Net force to the right direction will be equal F3 to the right, F2 is to the left. If I can calculate this difference, that will be the net force. Okay, so now I need to do the calculation for F2 and F3, right? So let's calculate this by using Coulomb's law. So how do you calculate F2? F2 is basically left particle and the middle particle, right? That means I have Coulomb constant, Q2, Q1, going to divide by distance given actually 0.20 and power 2, right? Just plug the numbers. This is Coulomb constant that will be given in your lecture note 8.99, 10 to the power 9 units Newton meter squared, Coulomb squared. I'm not going to write it since I do not have a lot of space here. And then next one is my Q1. If you use all SI unit, you don't want to write the units inside. Okay, make sure you use SI units. So now one more thing I need to do, this micro Coulomb should be able to write it in SI units. So I hope that also I discussed in the class. Micro Coulomb is equal to 10 to the negative 6 Coulomb. Okay, that's the conversion from your lecture number 1 for those units. Okay, so now I have, what are the charges I have? -4 and +3. Don't write this negative because Coulomb law does not include the sign into the formula. Coulomb law just explaining the magnitude only. Because of that, you're just going to write the number only. 4 times 10 to the negative 6. And now that I need to get a little more space. And times, next number I have 3 times 10 to the negative 6. I hope you can see it. 3 times 10 to the negative 6 and going to divide by 0.20 and power 2. So now you're going to plug that into the calculator and you will get the number as, I'm searching for the F2, I have around 2.7 newtons. And do the same for F3. Okay. Same for F3. F3 equal Coulomb constant. Now Q3 and Q1 divide by distance given 0.15 power 2. So now let's plug this in. Here 8.99, 10 to the 9. And then Q3 is 7 times 10 to the negative 6 because of microcoulombs. And Q1 is 3 times 10 to the negative 6. And you're going to divide by the distance power 2. Yeah. So this one, calculate, plug into the calculator, and I get 8.4 newtons. Okay. After that, I just go here and plug it. F3 is 8.4 minus F2 is 2.7. That means F net, I will get 5.7 newtons. F net to the right direction. So direction is needed for the vectors, right direction. Okay, so now let's move into the number 4. So now you are sitting certain distance from the point charge and you measure the electric field E. If your distance from the charge is double, what is the electric field is? So now if you have a charge particle, you measure the electric field here, right? And then you're going to measure the electric field here, double the distance. This is E new, and this whole distance is twice the distance that we had earlier. Okay, what is the electric field strength now? So now you guys remember that electric field is depend only this charge, right? Equal KQ over distance. In first case, distance is D and power 2. And when you go to the new E, only thing change is distance, KQ over 2D power 2. So let's rewrite this one. We have KQ over D squared, but 2 to the power 2 will give you 1 over 4, right? So what that means is, I have this part exactly in here. That means this I will be able to write 1/4 times E. 1/4 of E is your new strength. Definitely it's getting weaker when it go further away from the charge. Okay. So now next question is asking you to draw the electric field lines for positive charge, negative charge, and two opposite charge plates separately. So first one is positive charge. So electric field is basically starting from positive charge, ending with negative charge. Because of that, your electric field lines from the positive charge is going away from the charge. That's for the positive charge, right? And then for the negative charge, electric field line coming towards the negative charge. This arrow is important because it is a vector, and that's the electric field line for the negative charge. Okay, and it's very important that when I draw this, everything I draw it perpendicular to surface of the charge, right? So now my last configuration is two charge plates. One is positive, one is negative. We call it as the capacitor. If this one is positive, this one is negative, you know that electric field lines start from positive to negative. So that means your electric field lines will be this way. That's three configurations. Okay, now let's move into the number 6. This is about electric potential. So at location A, find the total electric potential. I need to find the electric potential at this point, right? Due to charge on the left and due to charge on the right. So now electric potential will be defined as Coulomb constant charge of the charge particle divided by distance to that charge, right? If I have many charges, I just need to keep adding each charge to this one. That means I can rewrite this formula if I want. From the Q1, it will do this, and Q2, it will do 2, and Q3 do 3, and keep moving. How many number of charges you have, you just keep adding it. But since we have only 2, we just need the 2 terms only. Okay. So now, since this is a scalar quantity, you definitely need to use the charge sign inside this formula. E and F you calculate earlier, we did not put the charge sign to that because direction we take separately. But potential is a electric potential is a scalar quantity. You're going to put the Q with the sign. Okay. So now let's calculate the electric potential at A point is equal. Coulomb constant is the common one. I'm going to write the from this particle, right? That particle charge is 8 times 10 to the negative coulomb, 9 coulomb. I'm going to write it 8 times 10 to the negative 9 coulombs, and going to divide by distance to that is this one, 0.20, right? That's the positive charge. And now you have the charge particle here. So now that charge particle is negative. Because of that, I need to write the negative charge. Don't write negative twice. The negative, this negative is the one that I took it into here. Okay. So now we have exactly same charge, 8.0 10 to the negative 9. And distance is important part. Distance, I need to get distance from here to here. That means I have 0.2 and 0.4. You need to add them. That will be 0.60 distance. Okay. Now let's plug the Coulomb constant and then calculate the electric potential in this case. So you're going to plug the Coulomb constant. You know what it is. 8.99 times 10 to the 9 newtons is in SI units for Coulomb square. And plug that and calculate the VA. Okay, you're going to do the calculation yourself. And the answer I get is around 240 volts. Okay. Voltage or potential measured by using units of volt. Okay, so now let's move into the number 7. We're going to move into the capacitors. What must be done to the capacitor in order to increase the amount of charge it can hold for a constant voltage? So if you take a look on the capacitor part, capacitor has the charge equal capacitance times the voltage, right? That means since you have constant voltage, that means you are not going to change the voltage. Only thing to increase the Q, you definitely need to increase the C, right? If I need the increment of Q, definitely I need to increment of C, right? So now C, we are not able to change. It is a manufacturing constant that can be changed during the manufacturing process. So if you take a look on the lecture part, capacitance is define it as some constant, there is actually two constant, times the cross-sectional area divided by the length of the distance between two plates, right? What that means is, if I have a capacitor like this, if you take the cross-sectional area and if you take the distance between these two plates, and this epsilon naught is the permittivity for the air, and K is the material insulator that you have inside. We call it as dielectric constant. Okay. So now to increase the capacitance, what should I do? See that? Increasing the C, I can definitely increase this, right? And I can definitely increase cross-sectional area, right? And epsilon naught is a constant, you cannot change it. But I can decrease the length between two plates. Those are the three things that you can change. Okay, one is increasing, you can write it in words, increasing dielectric constant. That means K. K value. Okay. And two, increasing cross-sectional area. That means A value in the equation. And third one is decrease distance between plates. That means B value in the equation. Okay. So now we're going to solve a very simple problem, including capacitors in parallel connection. So now this is called it as the parallel connection because you see that you have the this and this are parallel to each other, right? So that is we call it as the parallel connection of the capacitor. So other devices also, it is a parallel connection, it's parallel to each other, right? So you are learning two connections, one is the series and one is the parallel. So your question number 9 is series connection, question number 8 is parallel connection. You need to just identify those are parallel. After you identify they are parallel, you're going to use the parallel capacitor formula. Right, so if they are parallel, your equivalent capacitance will be equal to, you just add your all the parallel capacitors to that will give you the equivalent capacitance, right? So now this is simple. What I have is 0.1 plus 0.2 plus 0.3, no line microfarad. That means I have 0.6 microfarad as my final answer. Okay, now let's move into number 9. As I mentioned, number 9, they are series. So series means you see that ending of one capacitor is connecting to next capacitor, ending of that connecting to next, and keep going, right? That is called it as the series connection. So when you have series connection, you have to use capacitors in series, right? So you have formulas given for those. If they are series, your C equivalent will be equal to, you're going to take 1 over first capacitor plus 1 over second capacitor plus 1 over third capacitor, right? So now it's very important that you need to take the reciprocal at the end, right? So C equivalent equal 1 over 0.1, 1 over 0.2, 1 over 0.3, and then you're going to plug into the calculator and find the equivalent capacitor. So don't forget that you need to take the reciprocal at the end for your answer. So what I have is, I don't know if it's correct or not. I have very small number, 0.4 microfarad, right? So now it's very important that when you have capacitors in parallel, you see earlier, your new capacitance you are finding is greater than each of the capacitors that you are adding. 0.6 is greater than all of them. And here your equivalent capacitance is less than all of the capacitors, less than the 0.1, 0.2, and 0.3, right? That's important. Okay, let's move into number 10. So in the fabrication of electrical extension cord, manufacturer want to reduce the overall resistance. Now we're going to move into the resistance. Resistance is the basically, you can say the value that resists the current. Okay, slow down the current. Let's call it as the electric resistance. What changes should result to have the lowest resistance? So now you know that resistance also has a manufacturer formula that when they build up the resistance, they have to change some variables, right? So now rho symbol that I have here, we call it as the resistivity. That is basically you are changing the material. You can change the material if you want. Copper, aluminum, iron, whatever material that you need to use. That's the resistivity. And L is, we call it as the length of the resistor. And this is, as you know, this cross-sectional area. Right? So now if I need to increase the resistance, what you should do? So increase resistance. We say, want to reduce, sorry, we need to reduce. Not increase, we need to decrease. So you can think about the increase yourself. So you need to reduce the resistance. To reduce the resistance, one thing you can change is material. You can use the resistivity low material if you want. You can use resistivity low material, right? And you can decrease the L, you can decrease the length, and you can increase the cross section. Those are the 3 things you can do, right? What is the one? Decrease L. I'm going to write L here. You know what is L means. And increase A. And third one is use resistivity low material. Low material. Right, those are the 3 things that you can do. Okay, so now we're going to move into very simple circuits. Number 11. So I have a very simple circuit, resistance 4 ohms and 2 ohms are connected. Definitely you should know that these two are connected series when you come to here. And then what is the potential difference across each resistor? So now those questions can do it in different ways. But important thing you understand is this two has the series resistance, and then this 12 volt is the maximum voltage of the circuit, that 12 should be distributed to this and this, not equally, because they have different resistance, right? So now we need to think about the Ohm's law. So Ohm's law is saying potential of any resistor will be equal to current times the constant. That constant is the resistance of that resistor, right? So that means if I want to write it for the R1 resistor, voltage across this resistor will be equal to R1 times the current of that circuit, right? So now it is very important that this circuit will create the current. That current is going same around this loop. There is no possibility to change the current in the loop. If you have a single loop, it has the same current, right? So now similar to that, I will be able to write V2, that is for the second resistor, equal R2 times I, right? So now let's see the numbers. I have R1 times, R1 is just 4, right? 4 times I, and R2 is 2 times I. So as soon as you can see it in here, you can write your V1 is double of V2, double of V2, right? So as soon as you recognize that, what that means, this 12 voltage is distributed to these two, but the V1, that means the first resistor, have a double of the voltage that you have it on R2, right? So what that means? That means only possibility that I can have this 12 distribution will be 4 and 8, right? That means in this resistor, I should have the 4, and the other one, I should have the 8. So we should have 4 and 8 voltage, right? And this one has 8 voltage. This one has 4 voltage, right? Why is that? Reason is I already realized that my voltage of the first resistor is double of the voltage of the second resistor. That means only possibility that 12 can distribute is 8 and 4. That's the one way that you can think. So now let's write it in here. V1 equal 8 volt. V2 equal 4 volt. Okay. So there are different other ways that you can do. If you watch all the lecture, you know that how to calculate the current of this. And after you know how to calculate the current, you can plug into here. Plug into here, you can directly calculate V1 and V2, right? So that's part. After we calculate the current, we can come back to that in here. Okay. So now find equivalent resistance. So similar to the capacitors, resistance also can be connected series and parallel. When they are connected series, I'm going to review a little bit that. When you connect resistors series, that means you can have one resistor, you can have second resistor, you can have third resistor. How many number of resistors you connect in the circuit, it doesn't matter. R1, R2, R3. So if they are series connection, then we have the R equivalent equal R1 plus R2 plus R3, right? It's not exactly same as the capacitors. If you go to the capacitors, you definitely see that if they are series, you have to do 1 over formula in here, right? When you come to the resistors, you do opposite way. So now if you have parallel resistors like this, and like this, right? We'll say this is R1, R2, R3. So now this is, we call it as parallel connection. When they are parallel, this is where that you use 1 over R equivalent equal 1 over R1 plus 1 over R2 plus 1 over R3. So you need to identify which connection you have first, and then you need to use the way that you can solve the problem. Okay. Okay, give me a second. So there is something happening here. Okay, so now in this circuit, what we have? In this circuit, you will see on the circuit, right? In the circuit, I have these two resistors, these two, definitely series, right? So we're going to do the B, this is the extra L, and you're going to do the B here. So they are series. If they are series, we're just going to add them. R equivalent equals first one plus second one, that will be equal to 6 ohms. Okay. Okay, now my next question is finding current. How do I find the current of the loop, right? So now for this one, we know that the 12 volt is distributed into the R1 and R2 as we discussed in part A. So now I will be able to calculate the current by choosing the voltage that we have epsilon minus IR equals 0. We call it as the Kirchhoff rules, right? Epsilon is basically the battery, and I is the current, and R is the equivalent resistance of the circuit. Okay, so now we can easily do that. Battery voltage is given 12, and current is the one we need to find it out. R equivalent, we found it already, 6 equals 0. Because of that, I will be 12 over 6. That will give me I equal 2 amperes. Current is measured by using amperes, amps. Okay, so now after you find this current, as I mentioned in the part A, you remember in part A, after I find the current, you can see it in here. If current is 2, what will happen in here? 2 times 4 is 8. That means my V1 is 8. And 2 times 2 is 4. That is my V2 is 4. Okay, you can find the current first if you want, and then calculate the V. Okay, so now I have a concept question here. By connecting many light bulbs in the series, what can you say about will happen to the total current or the intensity of the lights? Do you think total resistance is smaller, greater, or than the largest resistance in this circuit? Explain. So you have light bulbs. Light bulbs, you use the symbol like this, right? Series connection. So now when you make the connection to the series, we say R1, R2, and R3 resistors. So now you know that when you have them series, you're going to get the larger value. So R equivalent will be equal R1 plus R2 plus R3. And it is greater than all R1, R2, R3. Is greater than all of them because you're going to add them all, right? What that greater means, when the resistance is greater, what will happen to the current? So what that means is current is lower. In other way, what that means, intensity is lower. When you have resistance are series or light bulbs are series, then your current will be lower and intensity will be lower. And do you think resistance is smaller, greater? Greater than all of them. Okay. So you can think about the same question for the capacitor, same question for the series and parallel capacitors, and series and parallel resistors. Okay. Okay, so now let's move into the number 12. Number 12, there is a circuit that you need to understand they are parallel to each other. So you have 5 ohms resistor and 2 ohms resistor. Connection is parallel. My first question is asking what is the potential difference across each resistor. So now it's very important in parallel resistance. You see that this voltage I supply will be the same for this and same for this. They have exactly same voltage. That voltage will be 10 for all. 10 volt for all. Same voltage for the resistors too. So now we need to find the equivalent resistance. As we know, since they are parallel, R over equivalent is equal 1 over R1 plus 1 over R2. So definitely 1 over 2 plus 1 over 5, and that will give you the net resistance, right? So now plug it to the calculator and then you're going to get the value. I'm going to probably do it in here, like take the 10 and then I have 5 plus 2 is 7, right? So 10 over 7, that will give me R equivalent equal 10 over 7. So that will be equal to around 1.43 ohms. Okay, so now we need to find the total current, right? Total current, we can write epsilon minus IR equivalent is equal 0. So now know that we have 10 volt minus current. R equivalent is 1.43 equal 0. And then you're going to find the I equal 10 divided by 1.43. That will give me around 6.999 amps. Okay, part D, if you add more lights, bulb, parallel to each other, what can you say about the current? So now you have some idea. When they have parallel to each other, right? Something like this. Now, when they are parallel, what will happen? Oh, sorry, parallel. So resistance smaller than all of them, R1, R2, R, all the parallel resistors will be smaller than all of them. Okay. When they are smaller, what will happen to the current? Current increase. Smaller means current will pass through or increase. And then what will happen to the other one? What is asking? Current and intensity. Intensity will be increase too. Okay, so last question. Determine the current in the circuit. Use the Kirchhoff rule here. So you need to use the Kirchhoff rule. So Kirchhoff rule has some important informations that is saying that especially Kirchhoff rules is designed for to solve the complex problem, complex circuits. But still Kirchhoff rule will be able to use for this simple circuit in your class, right? So Kirchhoff rule has some important thing. If you see if you see the formula that you have used earlier, that epsilon minus IR equals 0 is a one rule that is called it as the potential difference rule. That means if you start from one point and if you come back to same point again, as example, if I start here, If I walk through the circuit and come back to same points, your potential will be 0. That's what the potential difference rule. Other one is the current rule. So that means if you have any junction, current coming to the junction will be equal to current outgoing from the junction. So I in equal I out. So that is called it as the current rule or junction rule. Right, so in this circuit, since it is a single loop in your class, we definitely don't want the current loop, but we should know how to use the potential difference rule. That's the important part. Okay, so now when you use the potential difference rule, there are some of the things that I discuss in your class material, right? So when you see the circuit, first thing is you need to label the I. So since this circuit I is given, you see that I direction, this is the I direction. That means each of these wires I have I going clockwise direction. That is one thing. If it is not given, you need to label it your own direction, right? And second thing you need to label is your direction of the batteries, because batteries can connect in positive and negative direction. It's very important that you label the direction of the battery. In here you see that this is negative terminal, this is my positive terminal. That means this 24 is greater on the left side, right? And battery in here you see it is greater on the left side. That means that 6 is on your left side direction. Okay, and the other thing is you need to label the loop direction. Loop direction, again, it is your choice. You can label any direction you want, but you need to follow the your Kirchhoff rule. So let's say I'm going to choose the direction of the loop also clockwise. Choose the clockwise direction. Loop direction is my orange one, right? So now this formula will work this way. If your loop direction, right, loop direction and your current direction, loop direction and current direction, I'm going to use current direction as blue, loop direction and current and loop. Okay. If they are the same for the resistor, for R, then your voltage will be negative that current times R for the circuit. Okay, that is one thing. In addition to that, if you see the batteries, that means you have the loop direction and the epsilon direction. I have the direction of orange is the loop direction, and battery voltage direction, I label it in red. Okay. If they are in same direction, this is for battery. If they are in same direction, you have positive of the voltage, or we call it as epsilon, that symbol here, that's voltage. Okay. That's the rule, right? So now it's not that hard. So now you're going to start from the circuit somewhere you like. We'll say I'm going to start from here. This is my starting point. I'm going to end up the same point. So now when I walk to my loop direction is where that I'm going to walk through the circuit. So I'm going to walk through the clockwise direction. First, I will see the battery number 1. So that the voltage 24, and battery number 1, same direction as clockwise direction, because of that 24 is a positive number, right? And then I walk through, I don't see any device until I come to here. Now I come here, now I see the resistant current direction and loop direction will be the same direction. I need to subtract the I times the voltage of, resistance of that resistor to it, right? And then I walk through, next device I will see is the battery. Now I going from left to right, but my battery direction is opposite direction to the orange or loop direction. That means I need to subtract 6. Subtract 6. Okay, and then no device until I go to the 8 ohms here. Now my loop direction and the current direction is the same. That means I need to subtract I times 8 equal 0. Okay, so now 24 minus 6 is 18, minus I times 12, I times 8, that means 20 times I equals 0, and then you can calculate the I equal 18 over 20, and that will give me around 0.9 amps. Okay, so review number 13 one more time yourself and go back to the lecture part if you need more help. Okay, that's it for the worksheet number 10.